valuable, even though they are kind of abstract, just a pile of numbers. Then at the top, we have applications, how AI is actually integrated into the beating heart of businesses that deliver value to users around the world. So when we think about AI and we think about all that goes into making it possible for people to do new things with AI, we have to think about all of these different parts of the process. And today I'm mostly going to be talking about the models layer because that is what the Nemotron research project focuses on. Their sovereignty and their special data, their special ideas, their special platform, the way that they access their customers to help people solve problems. And so that's what Nemotron is going to be about. Now, I think when people consider Nvidia and Nvidia's work, they usually think about the chips layer because that's the thing that we sell. That's really exciting and something that's really important. The models that we're building with Nemotron, I think, are really important to the chips. We'll be talking about that as well. But that's where we're setting the stage today. So, where do we see AI models being headed? There's a few trends that I think are pretty important. The first has to do with scaling. I put it over here on the right, which is really about the way that compute is being used in AI and the need for more efficiency in building and deploying AI. So let's talk about that for a second. The original scaling law for AI had to do with pre-training. And the observation was that as we train models with more compute, bigger models, smarter data sets, the models become more capable. Now, this scaling law was originally a research result. Actually, some of the pioneering work on scaling laws happened at Baidu back when I was working there. And it was kind of an observation, an empirical observation, that the more compute we put into pre-training language models, the more accurate they become. And so if you extrapolate that out into the future, you could see even 10 years ago that there was a big possibility for this technology to become something really special. If you thought deeply about what does it mean for a language model to be more accurate, you start understanding that this means it's a generic problem-solving tool, right? Because you can ask a question and it can answer it. So that was the first scaling law. It had to do with pre-training. Now, since then, there's been several more dimensions of scaling that have emerged. The second one has to do with post-training. So pre-training is where we take a language model and we show it the entire internet and try to give it a basic understanding of all of the facts of the universe in every language, in every domain. But a pre-trained model is not actually useful for problem solving because it hasn't learned really how to interact with humans, hasn't really learned, how do we ask questions and how do we expect answers to be delivered. And so post-training is where we teach models how to be useful. And it is definitely the case that we see that as we increase the amount of compute that goes into post-training, the models become dramatically more useful. These days, we're using significant amounts of reinforcement learning, which is a very exciting thing. Reinforcement learning, for some of you that might know, is a very established and old theory about learning. And for many years, it was hard to get it to do something non-trivially useful. But with these models, what we found is that they can actually learn from basically experience. We put the models in environments, we give them the ability to try things out, and then we give them reward signals that are very sparse about whether they've succeeded at a problem. And it turns out that the algorithms and the models and the data sets and the environments have progressed to the point where this can actually yield non-trivial intelligence. The more time the model spends in the environment learning, the more it's able to solve problems. So that's the second dimension of scaling is post-training. Now, the third dimension of scaling happens when a model is deployed. We now have reasoning models that are able to try things out, try ideas out, and use that to solve a problem in the same way that you and I did back when we were children taking math class. You see a math problem, it's really hard, you're not really sure what to do. You try an approach, see how far you can take it. And if that works, great. But if it doesn't work, then maybe you think really hard. What kind of other approach, what other tools might I have that I could use to solve this? Give that a shot, push that forward, see where it goes. And you may have to try multiple times, right? So reasoning really has to do with kind of how many cycles of thought you can apply to a problem. And it makes sense that the more thought that you can apply to a problem, the more accurate, the more useful the solution is going to be. So that's a third dimension of scaling where we can turn compute into intelligence. The fourth dimension, which is coming about just now, has to do with agentic systems. LLMs are general intelligence, but if we put them in harnesses that allow them to interact with the world and interact with problems that we pose to them and let them go ahead and try to solve them, it turns out that you can get some really amazing results. And over time, we believe every one of us is going to become basically the CEO of a company filled of agents that are working on our behalf, trying to solve the problems that we face. And again, this is another dimension of how compute is transformed into intelligence. Okay, so 4 different dimensions of transforming compute into intelligence. It's very exciting, but it's also very daunting. This is the biggest challenge that computing has ever faced. It's the biggest opportunity and the biggest challenge at the same time. How are we possibly going to find enough compute to make any of this possible? And for those of you that work in AI, everyone in this field is facing this problem. All of us need more compute because it's very clear that the more compute we have, the more intelligence we have, and our research, our ability to connect our ideas to impact and help solve problems directly tied to compute. So if we assume that we're just going to get as much compute as is possible for us to get a hold of, limited either by economics or by physics, whatever, there's some sort of limit, we're just going to have as much compute as we can get. Then what it becomes obvious is that efficiency then is also directly connected to intelligence. Because with a fixed amount of compute, if we know that the more compute you have, the more intelligence you have, the only option is to increase the efficiency of AI if we want more intelligence. And so that, I think, is really, really important observation about the future of artificial intelligence. All of the innovations that go into increasing the efficiency of AI are going to make AI more useful and more intelligent. And specifically for those of you, I'm not sure what each of you are working on. I would expect, given the amazing talent in Korea regarding fabrication of different things, including semiconductors, that some of you are interested in different kinds of techniques that can create efficiency in different ways. All of them come together to provide intelligence. So all of them are very, very important. All right, so efficiency is becoming key for artificial intelligence, but there's also some other trends that are going on. The second one I wanted to highlight has to do with specialization. AI is a very general purpose tool. The way that we train these models, show them the entire internet, have them learn everything, every fact in every domain, and then try to make them general problem solvers, trying to teach them how to use every tool. In post-training, we're trying to increase the number of environments to as large as possible, so they learn how to code in Python, they learn how to solve math problems. They can do all the things that we're trying to teach them. But when we think about the way that AI is deployed, AI is changing how we work in every field, in every domain. But that means it needs specialization. And the reason for that is really simple, that every company, every organization is already solving problems in its own way. It has its own problems, it has its own customers or the people it's trying to help. It has its own means for doing that. It has its own data. And, AI is dramatically more useful when it's given the most important, most valuable data. But it's also true that the most important and valuable data always is the most carefully guarded. So, for example, in my life, I think about my most important data, my text messages, my photos, my financial records, right? These things are very valuable to me, but I don't want to just post them online for all of you to read. That wouldn't be great, right? And vice versa, right? Everybody needs privacy. So in the same way that all of us need privacy, every company, every organization needs to be able to interact with its most valuable data in a way that preserves its privacy, that preserves its platform and its relationships. And that leads to this need for specialization. We want to be able to make it possible for a bank to think about AI in a different way than a hospital. Both banks and hospitals are going to change fundamentally because of AI, but the way it's going to happen is quite different. The way that a hospital integrates AI into the work that it does is going to be quite different than, let's say, a grocery store or a farm. And all of them have secrets and have special ideas, special platform. We want to help make that possible. So that drives this need for specialization and tight integration, AI that's tightly integrated into the beating heart of the business. The last thing I wanted to highlight is about AI is becoming a system of models rather than a single model. And this is already every day. This is an everyday occurrence. For example, if you use ChatGPT and you ask it a simple question, today it'll use 5.3. But if you ask it a complicated question that needs a lot of reasoning, it'll use 5.4. Why is that? Well, it's because the cost to serve a simple question should be less than the cost to serve a complicated question, right? And I just was talking about efficiency and how efficiency is intelligence. What that means is that we need systems of models that have different capabilities so that we can maximize efficiency. Maximizing efficiency is maximizing intelligence. So this means all of these things together, that AI is not a one-size-fits-all problem. Although AI is a general technology, the way it's going to be built and deployed is going to be quite diverse. And it needs to be diverse because the world is diverse, because the problems we face are diverse. And so that's motivating a lot of the work that Nvidia is doing to support the AI ecosystem. Nemotron is what we call our collection of core AI technologies. It includes models, as well as data sets, techniques, and software. So I'm going to be talking about that today, and the different things that we're trying to bring to this ecosystem. Now, Nvidia is a different kind of AI company than most of the other big AI companies that you may know about, because we work with everyone. We work with AI native companies. We work with established enterprises. We work with companies in Europe, companies in Asia, companies in the United States. We work all over the world in every part of the economy. And because of that, our business is built in maybe a different way. We are very excited about all of the AI models that are out there. We love it when new AI happens. Whenever something good happens in AI, that's an opportunity for Nvidia to grow our work, because that's just the position that we have. So what that means is that we're not trying to control the way that AI is built or deployed. We're trying to support the ecosystem. And because of that, we want to be very open in the way that we're building AI. We want to provide those data sets in an open way so that other organizations can build AI that serves their own needs, specialize AI in a way that helps them. We want to put all of our techniques out there. It turns out that building AI is a very empirical problem. There are a lot of choices ranging from things like learning rate schedules to batch sizes to the way that we sample during rollouts and post-training that require a lot of experimentation and are quite expensive in order to actually figure out how to do. And so most of the AI organizations that are out there building AI can't really share the results of all of those studies because they're just too expensive to create. But for Nvidia, although they are very expensive for us to create, we know that if we help the ecosystem grow, if we help other engineers and researchers build the future of AI, then that's an opportunity for us. So we want to do that. We want to be open about that. And the same with data sets. Data is really the foundation of AI, and we know that as we increase the strength of our data sets, as we maximize the intelligence in our data sets, that the AI also gets stronger. And so we are able to release our data in a way that actually helps other companies build and deploy AI for themselves. Okay, so I've been talking about Nemotron. I've been talking about what it is. Now I'm going to tell you why we're doing it, and there's two main reasons. The first has to do with NVIDIA's core business of building systems for AI. In order for us to do that, we have to know what AI is. We have to understand deeply all of the things about AI in order to build systems for it. I'll be talking about that in a second. And then the second is that we want to accelerate the ecosystem. We want to make it possible for companies around the world to build and deploy AI. And so that's the job that we have set for ourselves. Okay, so talking about accelerated computing, one of NVIDIA's this is the work that NVIDIA does. When we get up in the morning and we're thinking about what we're building, what we're trying to do is think from first principles about the most important computational problems the world faces and then figure out how to make it go faster. And Nemotron helps us do that. So let me explain a little bit. One example would be mixture of experts architecture. So neural networks these days, many of the AI that you interact with every day are built from an architecture called the mixture of experts, which was invented at Google. It is a really interesting idea. It creates a lot of sparsity in the neural network. And because it creates a lot of sparsity, it actually places a lot of demands on the networking that is used to both train and deploy these models. So NVIDIA was looking at that, and we realized that the importance of mixture of experts models was going to change the way that we interconnect all of our processors. And so for the Blackwell generation, which our current generation of GPUs, we actually created something called NVLink 72, which allows for 72 GPUs to read and write each other's memory sort of randomly and dynamically at very high speed and low latency. And this was a big bet that we made. It's actually a technical challenge. It's very difficult to build a system that has this kind of interconnect. The software is very complicated. The resilience and reliability features that are necessary to make this actually work, very complicated. But as a result, Blackwell has enormous advantages when both building and deploying mixture of experts models. And so, if NVIDIA didn't know a lot about the structure of these neural networks, we couldn't have built Blackwell. So there's one example. Another example has to do with numerics and sparsity. So we have put a lot of advanced features into the GPU to be able to train and deploy models with reduced precision arithmetic because it saves a lot of energy. And remember, efficiency and intelligence are the same thing. So if we can make something more efficient, we can then make it more intelligent. These days, actually, we are pre-training our Nemotron models using 4-bit arithmetic, which is quite a technical challenge, and I'll be talking about that a little bit more later. The reason why we're doing that is because we know that if we can push the field forward, if we can figure out how to use reduced precision arithmetic in new ways, then we can increase efficiency and we can increase intelligence. Accelerated computing is a lot more than just the chips. It also has to do with data sets and with the algorithms. So what do I mean by that? Well, in our pre-training work, over the past year, we have accelerated the time that it takes for an LLM to reach a given level of intelligence by a factor of 4 because our pre-training data set is much smarter than it was a year ago. We spent a lot of time using a lot of compute, basically sifting through the entire internet to find the parts of the internet that actually help neural networks learn. It turns out that not every bit of data on the internet is as smart as every other bit, as you might expect. And so if we can figure out where the smart parts of all of our data are and then pull those out in a way that helps the neural network learn, that actually increases the speed at which people can build AI. You know, a factor of 4 faster year over year on the exact same hardware with the exact same software, that's much faster than Moore's law, right? And these days, Moore's law is effectively dead, right? We're not going to get a 2x increase year over year or every 18 months, depending on how you define it. We're not going to get that from simply turning the crank on the transistors. We have to have smarter techniques. We need to think about the problem from first principles and optimize the whole thing. So data sets are now part of accelerated computing. Algorithms are part of accelerated computing as well. I'm going to be talking later about Pivot RL, which is an algorithm that was developed by Alexi's team. Alexi's up here with me today, that accelerates post-training by about a factor of 5 because it's smarter in the way that it uses compute to train a model. So again, really dramatic speed ups that come from smarter algorithms. Another aspect of acceleration these days has to do with conciseness. So if a language model is answering your question and it takes, let's say, 10,000 tokens to answer the question, and another language model answers the same question with the same result, but does it in 1,000 tokens, that's like a factor of 10 in speed and also then in efficiency that's different. So that means that a critical part of accelerated computing these days is training a language model how to be concise when it answers a question. Again, this is really far away from a chip, right? But if you think about it, the job that Nvidia faces, you know, we're an accelerated computing company. It's not, a chip could never be enough to solve the world's computational problems. In order to do that, we have to think about the whole thing. And so that's the first job of Nemotron, is to help Nvidia think through these issues from first principles so that we know how to build the systems, software, the hardware that the world needs to build AI. Now, Nemotron is built as, you know, with this accelerated computing principle in mind. We think about Nemotron with 3 different criteria in mind. The first is that faster models, more efficient models are smarter models, which I've already explained. The second is that we're building for systems that we want to run fully loaded. This is really about making sure that if you deploy a model, you get the maximum amount of intelligence from that hardware. That you are running that system at full tilt all the time, and so that's the design point that we focus on. And the third thing is that we build Nemotron for specific systems in mind. So we think about the hardware, that we're going to target, and then we co-design the model to fit that particular set of hardware. So those are these kinds of the reason I'm telling you all this is because I think when you look at Nemotron, when you look at Nemotron models, when you look at the research program behind Nemotron, it makes more sense if you understand the context that we're coming from and the problems that we're trying to solve. Nvidia being a different kind of AI company, we think about problem of building AI in a slightly different way. Now, Nemotron is open. It's part of Nvidia's open family of models for AI. Nemotron is our core reasoning technology. We also have some other key initiatives. We have Cosmos, which is really about building models for physical AI, and Brute, which is about models for robotics. We don't have this on the slide, but we have our models for self-driving as well that are open, called that Alpamayo, which is named after a mountain in South America. We have Clara, which is our models for biomedical AI. And we've really stepped up our investment in open source technologies for AI over the past few years. This graph here is showing that impact. Looking from the end of 2024 through the end of 2025, you can see how NVIDIA's contributions to open AI on Hugging Face have been outpacing other institutions around the world. And we're really proud of that. We're proud that we can do that. We're proud to see other people building on the things that we've been putting out into the world, and we hope to continue doing that. And the reason for that, this is Nemotron's second job. You know, I said Nemotron's first job was help NVIDIA build systems for the future. NVIDIA's second job is to accelerate the ecosystem. You know, when you work with NVIDIA to build AI and deploy AI, you have an enormous advantage because NVIDIA's ecosystem is everywhere and it's very rich. You know, you can use any kind of AI that you can dream. You can invent new kinds of AI. You can run on the cloud or on premise. You can work with many different cloud computing providers in order to get access to compute. That value, that option value that comes from this ecosystem is really important to us. And we feel like in order to continue developing that, all of this open source AI technology is really necessary. You know, you think about being a startup or actually even a big company that's trying to think about how to customize and integrate AI into the beating heart of their business. You know, if they can start from open source technology and customize it, that really opens up opportunities for them that we think are important. So that's why we're making these contributions. Now, Nemotron, we announced a few weeks ago at our GTC conference in San Jose. Nemotron is being developed in a coalition moving forward. So, you know, this is kind of a new idea. It's a difficult idea, but I think something that's really good for the industry is to think about how can we combine our ideas and our compute and all of our intelligence to build a foundation that we can share to advance the AI ecosystem. And so we announced that we're building the future of Nemotron in a coalition with several other companies. Over time, I expect that this list of companies is going to grow as we prove out this model of building amazing AI as a group, you know, as opposed to just something that we build inside of one company and then put on the internet. How about we build it together and advance the ecosystem together? Something that I think is really important. Okay, so I've been talking about the motivation. What is Nemotron? Why are we building it? Why is it important to us? Now I want to talk about the technology in a more specific way. So we have been releasing the Nemotron 3 model family over the past few months. We started with Nemotron Nano, which we released in December. It's a 30 billion parameter model. It's a mixture of experts, so that means it's sparse, and there's only 3 billion active parameters out of those 30 billion. Next, we released our medium-sized model, Nemotron 3 Super, which is 120 billion parameters. We released that a few weeks ago. And then coming soon in the next few weeks is going to be Nemotron Ultra, which is about a 500 billion parameter model. Now, you know, each of these Nano, Super, Ultra, the models get better as they get bigger. That's the idea. But we also have other dimensions of AI that are important. We have Nemotron Omni, which is really about multimodal reasoning. We're going to be releasing our first Omni model very soon. That's a model that can understand text, image, audio, and video and reason about it and produce text. So you can ask, for example, a question about the contents of a video, and the AI can watch that video, listen to it, and then answer a question. We also have speech models, including full duplex models that allow for people to have much more natural interactions with AI. This is really important because when we think about, you know, all of the 8 billion humans on the planet and the ways that they interact with AI, many of them are going to prefer interacting with speech and images rather than just with text, because, you know, reading and writing isn't very fun sometimes or very natural. And so we care a lot about the user interface for AI as well. We also have things like specialized models for retrieval augmented generation, so that businesses can provide intelligence based on you know, piles of documents, documentation, you know, legal documents or product description design documents, for example. These you know, technologies all come together to make Nemotron. Okay, I want to talk in a lot more detail about the technologies behind our most recent model, Nemotron 3 Super, which we released a few weeks ago. We are really proud about the combination of intelligence and efficiency that we achieved with Nemotron 3 Super. On the top right, this graph is a little bit small, so it might be hard to read, but the x-axis has to do with throughput per GPU. So this is basically like how fast is the model, and the y-axis is intelligence based on the artificial analysis index. So for example, if you compare Nemotron 3 Super to GPT OSS 120B, the open weight model from OpenAI, Nemotron 3 Super is a little bit more intelligent and quite a bit faster. And that's something that we're pretty proud of. It took a lot of invention to build that. And I'm going to be talking about how we did that. The first is that we used a hybrid MOE architecture. I'll talk about what that is in a little more detail in a second. Second is we used multi-token prediction so that we can predict multiple tokens at every time step. So you stick in one token, the model can predict multiple. I'll talk about that as well in a little bit more detail. We have a context length of 1 million tokens. This is an effective context length, so this isn't a theoretical context length of what could fit on the machine. This is actually like a useful context length. And 1 million tokens is an awful lot. That makes the model really good in a lot of applications that need that context length. We also have latent MOE. This is latent. It's a way of thinking about mixture of experts that actually creates more efficiency at inference time and makes the model capable of working with more experts at the same compute cost. We also, for Nemotron 3 Super, we post-trained it using Nemo RL Gym, which is really key. This is a software that we're building with all the environments that are necessary for post-training, really increase the utility of this model. So all these things come together to make Nemotron 3 Super. One thing we were really proud of is that there was a new benchmark for agentic tasks called Pinch Bench that was released at about the same time that we were releasing Nemotron 3 Super. We'd never seen this benchmark before, but it turned out that we were the #1 open model in the world when this benchmark was released, and we were up there beating a lot of the proprietary frontier models at the same time. And this is a benchmark we hadn't even optimized for, so that was pretty exciting for us. All right, so I wanted, since this is a university and some of you are involved in creating AI yourselves, I wanted to talk about these technologies in a little bit more detail. The first has to do with the neural net architecture behind Nemotron 3 Super. It is built out of what we call a hybrid SSM, mixture of experts. What does that mean? Well, the most language models started with the transformer. The transformer, as you might remember, comes from a paper. It says attention is all you need. And it describes an architecture where the model is able to turn its attention over sequences to particular tokens dynamically as it reasons about a sequence. Now, attention is a really powerful technology. It has been fundamental to modern AI. It's also an expensive technology because the amount of work that it takes to think about an entire sequence scales with the length of the sequence. And so what that means is that as you're processing a sequence, this actually becomes a quadratic algorithm because every time you add a new token, you have to look at all the previous tokens. And then you add a new token, you have to look at the sum of all of those tokens, and you keep doing that. That's actually a quadratic algorithm. So that's going to become very expensive. Now, there's this idea called state space models. It's kind of an evolution of recurrent neural networks from back in the day, if you remember the LSTM or things like that. The thing that's really attractive about state space models is that they have a linear cost. As the sequence length gets larger, the amount of time it takes to process that sequence is just linear. It doesn't get bigger as the sequence gets longer. But there's always these questions like, well, can it actually be as good as attention? Because the advantage of full attention is that no matter what information is in the sequence, the model is able to find it, right? Because it has the ability to look at every single token, no matter what. And so we actually did some research in 2023, published a paper in 2024 that has this graph here at the bottom that is showing the validation loss on the y-axis, and on the x-axis is the percentage of attention layers, okay? So if we go to 0%, that means it's just a standard full SSM. So there's no quadratic attention at all. It's just a linear attention method, okay? And we get a certain loss. If we go all the way to the right, which is 100% attention, that's a standard transformer. It's just every layer is built in the standard way as a normal transformer, and you get a certain validation loss. Now, the interesting thing is that the full SSM model loss is a little bit better. So if you look at 0, it's a little bit better than the full transformer loss at 100, which kind of says that the state space model is actually a little bit better than the transformer in general. But there's a much more dramatic improvement if we go to a hybrid model that uses both. And so you can see at about 7–10% that we have a much better validation loss, meaning that we have a much better core language model. And we've gotten most of the computational benefits of the linear attention from the SSM because we've reduced the quadratic attention by at least an order of magnitude. Now, the things in the middle here are still quadratic algorithms, right? It's just that the constant on the quadratic term has been pushed down by like an order of magnitude. And so this finding that we had a few years ago that hybrid attention and state space models was actually better than either of them really has motivated a lot of the work in Nemotron architecture. And other organizations have seen this as well. I don't know if you noticed, QN has moved, all the recent QN models are doing this. Kimi is also doing this. Olmo, the open model effort from the Allen Institute, just published a paper a couple weeks ago that confirms this finding. And this has, I think, pretty important implications for the efficiency of AI because these hybrid models can be dramatically more efficient and more accurate. So we take this observation and then we use that to build the Nemotron 3 architecture, which is this diagram at the top. We have some amount where it says Mamba 2, that's a state space model. When it says latent MOE, that's not attention, that's just processing the token using a mixture of experts layer. And then where it says attention, that's the full attention layer from a transformer. So we're kind of building these building blocks that have a small amount of full attention and a lot of state space sequence modeling. And then, we get a lot of efficiency gains from that. Now, another innovation in the Nemotron architecture has to do with something we call latent MOE. Now, some of you may know the way that mixture of experts works is that basically you have your parameters, but each token is only going to be processed by some small fraction of the parameters. It's a sparse technique. And what we'd like to do is make it more sparse, but also have the ability for more parameters to work on a single token so that we can have more opportunity for the things we've learned during training to impact the results. The model can be smarter. And what we realized is that there is an opportunity to do this by by taking a technique that's very simple. We just down project. So if you look on the right, after attention, we have this router that's deciding where a particular token's going. And then we down project that output before we do the dispatch. What that means is that we get to save a lot of communication. When a model is deployed, it's usually deployed on many GPUs, and we partition the experts across multiple GPUs, which means that we have to route the tokens between all of the GPUs dynamically based on what the router decides to do. And so because we do this down projection, the amount of data that we have to route around is much smaller. So we down project, we route, then we do the processing and the mixture of experts, we combine it, and then we up project it back into the same dimension that the model uses. So we call this latent MOE because we're operating in a latent space that's smaller than the standard space of the model. And this effectively gives us the ability to talk to 4 times more experts for the same amount of compute, which makes the model smarter. And remember, more efficiency is more intelligence. All right. Another thing I wanted to talk about is multi-token prediction, which we built into the model from the beginning. Now, the idea behind multi-token prediction is pretty simple. In a standard LLM, you put in a token, and then, or you put in a question which has maybe in context, so maybe whatever, however many tokens that could be. It could be thousands of tokens. That gets all processed. But then the most expensive part of inference is what we call autoregressive generation. So the model produces a token, and then that comes from the output of the model and goes back into the input, goes all the way through the model to produce another token, goes all the way from the output to the input, and we do this token by token. Okay. Now the problem with doing this from a computational point of view is that it's very bandwidth bound. You have this expensive processor that has a lot of math throughput, and most of the time it's just waiting for the weights to stream in from memory. The weights are very big; they can't fit on the chip, and so we have to stream them in, and that means that all of the math units are just sitting there waiting for something to happen. So what if we could predict, instead of one token, what if we could predict multiple tokens into the future? And then we could take those tokens, let's say we have a group of, let's say 3. Then instead of putting one token in, we put in 3 tokens. It's actually going to cost about the same to do inference with 3 tokens as 1, because remember, we're mostly just waiting for the weights to stream in. So the math units are basically free, so we can basically verify. If it turns out that those 3 tokens, that they were predicted correctly, then we can accept them basically for the cost of processing 1 token, which then gives us a speed up of like 3x, right? So that's the idea behind multi-token prediction. And in this graph, you can see that it's actually working. This is comparing several different models, Nemotron 3 Super against a QN model, against DeepSeek R1, and the x-axis is how many tokens we're predicting, and then the y-axis is the actually correct prediction. You can imagine as we predict farther out into the future, the probability that we predict correctly goes lower, but we have a pretty competitive multi-token prediction system here. And this is going to be context domain specific, right? So on the right, we have average acceptance lengths on a benchmark that has multiple different domains in it. And you can see that the number of tokens that we predict correctly is going to vary by domain. Some domains are easier to predict multiple tokens than others. This chart, I think, is a great example of why accelerated computing really requires understanding AI deeply. If Nvidia was building hardware for multi-token prediction, but we didn't understand that it was domains dependent, we wouldn't be able to actually figure out how to make hardware that our customers could use. So we have to understand all these details. Now, the other thing that's important about multi-token prediction that we also showed in this project is that makes the model more intelligent. It's actually just a better loss function. When you train a model and you give it this objective to predict multiple tokens at once, it actually forces the model to build up richer internal representations of the problem, which then makes it just better at reasoning, makes it a better language model. So multi-token prediction makes the model smarter. It also makes the model faster. All right, so with Nemotron 3 Super, we actually did pre-training using 4-bit arithmetic in a hybrid mixed precision kind of way. Now, this is something very ambitious and challenging to do because 4 bits is not a lot of bits in order to represent the weights and the activations of a model during training. Now, it's not actually 4 bits, it's actually 4.75 bits. The actual 0.75 extra bits matters a lot. This representation is kind of interesting. It has some scale factors per block, and all of this is hardware accelerated. So the choice of this format is something that requires a lot of research. And then the way we use it to train a model also requires a lot of research. So what you can see is that all of the linear layers we use FP4, except for the final 15% of the network, we use FP16. Why did we choose that? Well, we did a lot of experiments and we found that without this, the model wasn't stable. Latent projections, I talked about the latent MOE, we're projecting up and down. Those we left in bfloat 16 because it didn't actually matter and it was just better to not worry about it. The MTP layers also needed to be in bfloat. This was empirically discovered that MTP just didn't work if we used FP4, at least with that particular algorithm. Attention projections also needed to be in FP16. The state space model output projection we did in MXFP8. And then the embedding layers that convert tokens and like inputs into token IDs into inputs to the model, and then also on the output side produce tokens. Those needed to be in FP16 as well. Now, there's a lot more that went into this than just figuring out what precisions each layer needed to be. We also are using extensive use of randomized Hadamard transforms in order to spread out activation spikes in the network. This is a numerical technique. It's an invertible technique that kind of smushes variance around. If you have a distribution that is very peaky, you can use one of these randomized Hadamard transforms to transform it into a vector that's much less peaky, but it's invertible, so that you can do this transform, make sure that you don't have to clip any of the values with your very restricted 4-bit format, and then undo that right before you need to in order to preserve the values in the computation. So there's a lot of algorithmic work that went into making this possible. Okay, talking about post-training, the post-training for Nemotron 3 Super was pretty involved. We start with a base million token context model that hasn't been post-trained. Then we do supervised fine-tuning. This is really where we show the model examples of problems and solutions, and the model starts getting better at understanding how problems are stated and what solutions look like. Then we do reinforcement learning with verifiable rewards, where we have a curriculum with multiple rounds. We increase the richness and diversity of the post-training as we go. And then we do some specialized reinforcement learning for software engineering tasks. Then we do reinforcement learning with human feedback. And then we do our multi-token prediction healing stage in order to produce the model. So this is a fairly complex pipeline. It has a lot of moving pieces. And again, we describe all of this in detail because we want other people to build on it and make even better AI. Part of Nemotron, it's not just the model, it's the techniques, and we're being open about how we do this to help the community. Okay, so all of that made Nemotron 3 a great model that we're really proud of. We're also working on Nemotron 3 Ultra. This is going to be one of the leading open frontier models in the world when we release it. We're very excited about it. The pre-training finished and it got great results. We're comparing against the leading open base models that are out there. It turns out not a lot of organizations release base models, and so these comparisons are a little challenging to do. And you might ask, well, why is GLM 4.5 on here? I thought they were on 5.2 or whatever the number is today. And the answer is because they haven't released the base model after 4.5. And same with Kimi K2. But nonetheless, we're really proud of the accuracies. These are base model benchmarks. We're really proud of the accuracies that we've achieved, and the model's currently in post-training right now, and we can't wait to release it soon. All right, I just wanted to wrap up the talk with a few other ideas that we've been working on as part of the Nemotron effort. One is a data set that we have released recently called Nemotron Personas Korea. And what this is a collection of data about 7 million personas. These are synthetic identities where there's no personally identifiable information that's connected to any real person, but it's information that's like a real person. Grounded in real-world distributions, permissively licensed, to help Korean AI developers have access to a data set of information about personas that can be used to make their AI models more useful for real information, but again, without actually including any personal information. So we were really happy to do that. I think we're going to be continuing to make synthetic data sets for various targeted needs like this one going forward. And then I wanted to talk about a couple of research projects that that we were pretty proud of. The first is Pivot RL, which we used in post-training of Nemotron 3 Super and Ultra. The idea here is we want to accelerate post-training. We want to make post-training more efficient. Again, more efficiency is more intelligence. And what we realized is that during reinforcement learning, when we're sampling trajectories, a lot of the trajectories are very easy to predict. A lot of the tokens in the trajectories are very easy to predict. There's only a few tokens where the model has to make a choice. You think about when you were taking a test, a math test as a student, you try tactic A, push that far, then maybe it didn't work, try tactic B. At these points where you're trying to decide what tactic am I going to use to solve the problem, we call those pivot points. And that's where we want to use RL, we want to use our sampling budget, we want to use our compute budget to sample from these different tactics. Once you've decided a direction that you're going to go, it's usually a lot more predictable. So rather than having to sample every token, we only have to sample the important pivot points during the trajectory. That can save a lot of compute. In this case, we're about 5.5 times faster in terms of wall clock time to get to a given level of accuracy. And since all of us are constrained in the amount of compute that we have, this is a really important capability to reduce, to basically use our compute more effectively, make more intelligence. We also have a post-training project called Nemotron Cascade. This is really about a curriculum. It's about developing a curriculum that helps a model learn how to problem solve in more intelligent ways. And we applied this curriculum to our Nemotron 3 Nano model, which is a 30 billion parameter model, and got some really amazing results. This model is only the second open source model in the world that can achieve gold medal accuracy on the International Math Olympiad 2025, as well as the International Olympiad of Informatics and the ICPC World Finals. The only other open source model that could do that when we released this research was DeepSeek 3.2 Speciale, which is a 671 billion parameter model. So the fact that we were able to make a 30 billion parameter Nemotron model perform with this kind of skill, I think is a reflection of how important the curriculum is in order to make models good at problem solving. And this training pipeline that's here on the bottom left kind of indicates how that works. It's similar to what we use to do Nemotron 3 Super, but with a little bit of maybe one of the differences has to do with the order in which we do things and then the way that we combine skills. So with Cascade, we actually do something called multi-domain on-policy distillation, where we teach the model how to be expert in a number of different ways. And these models we now have a collection of models, each of which is good at one particular subtask. The question is, how do we make one model that's good at everything? And the idea is that we use on-policy distillation from multiple teachers in order to create a single model that can do all of those skills in one model. So that was a kind of a different way of thinking about how to build a model, and we're pretty proud of the results that it got. Okay, so I'm coming to the end of my remarks here. I hope there's a couple of objectives that I had with this talk today. The first is to explain to you what NVIDIA's model work is. Explain that it's more than models, it's also the techniques. We're trying to be very open about what we're doing. And the reason we're doing that is because it's really connected to our needs as a company. We're trying to do two things. First, figure out how to build the systems of the future. We have to have Nemotron in order to do that. And second is to figure out how to enable the ecosystem so that people around the world can continue developing and building AI in ways that they get to control, and using their unique insights, their unique position in the world to make AI that matters for everyone. And we know that both of those things are core to NVIDIA's work, that they're core to NVIDIA's future, and that's why we're building Nemotron. And then, I guess the second thing that I wanted to get across was just, since this is an academic audience and a lot of you are involved in this technology, I wanted to give you a little bit more details about the technology itself, and kind of some of the insights that we've had. We are very grateful for the academic community and for the things that we learn from you. Many of you publish papers at the same conferences that we attend. We're very excited about the good ideas that academia has about advancing AI. We learn from you. We try to incorporate this into our work, and then we try to publish what we're doing so that we can hopefully inspire the field to continue to progress. I wanted you to get a sense of that as well, because I think there's a lot more work that we need to do as a community to push AI forward together. So with that, I'm happy to take any questions.
Well, great talk, and also releasing this such a great resource for the AI researchers and practitioners. And it's now is the time for Q&A. So if you have a question, please raise your hand. Please identify yourself and then your affiliation, your department before asking questions. And also 그다음에 좀 민감한 그 다른 회사에 대한 질문은 사양해 달라는 얘기가 있었습니다. So please be considerate. Yeah.
Hi, thank you so much for this talk. I'm Ray. I'm a researcher in the computer science department. I had two questions. I'm not sure if that's allowed, but the first question is about the 2024 study about hybrid between SSMs and transformers. I think you noted that the full SSM has lower validation loss than the full transformer, but naively we would predict that the full transformer was better. So I was wondering if you knew the reason why the full SSM performs better in that experiment. And my second question is about the synthetic data set for Korea. Could you talk a little bit about how the synthetic data set is created? Like, how do you create a synthetic persona? Are they all drawn from the same probability distribution, or what does that look like?
Yeah. Okay. So about the first question, if you read the literature on state space models, the argument has always been that a state space model can come up with a richer understanding of a sequence because it's kind of building up an iterative understanding of the whole sequence in one place. So basically the compression, like the ultimate goal of sequence modeling is to understand a sequence, and the fact that the state space model has to cram all of that information into a constant, basically summarization of the sequence should be a more powerful representation than just having the ability to look at arbitrary points during the sequence. So that's kind of the intuition behind why state space modeling might be more powerful, but it does give up the ability to actually find individual tokens, and so I think that's the intuition of why hybrid models are best. To your second question, we have a project regarding synthetic data generation. It's very complex, and so the details I think are maybe more than we can cover in an answer like this, but it is the result of several years of work that we've been doing in order to build models for synthetic data generation that can help build data sets for AI. And we've seen that these kinds of synthetic data sets are very useful for our work in other languages, and so we felt like we should do one for Korea, which is why we're releasing this one.
Hi, my name is Sojun, and first of all, thank you for coming to SNU and giving an awesome talk. So my question is that I heard that from your Fortune interview, I heard that even your group at Nvidia is GPU constrained. So given that, what kind of research projects do you believe that still university labs still are good at, and what kind of research we shouldn't compete on with other industries?
Yeah, it's a great question. I think everyone is compute constrained around the whole industry. No matter how much compute you have access to, you're always compute constrained. Now, what is the implication for academia? Academia has always been best when it provides new and surprising ideas that help the industry rethink the way it does its business. Academia has never been best at large-scale industrial production. For example, if you're working in the mechanical engineering department and you think that your job is to teach Toyota or Hyundai how to build engines, probably that's not a good thing. But new research on combustion, that's a really good thing, right? Because it turns out that the science behind how to build an engine is something that is very challenging. We don't actually know everything about. So it's a strange thing actually in computer science that there was a time, let's say 10, 15 years ago, when academic research often yielded state-of-the-art results in a particular field. Why is that strange? Well, that's not how it usually works in academia, right? If you're in the mechanical engineering department, you don't try to build bridges that are the biggest bridges in the world, right? But you do study the science behind bridges. There's definitely new ideas about how to build a bridge that the people who build the biggest bridges in the world haven't thought of before. So the challenge for computer science in the modern era, where AI is a very large-scale industrial activity, is to focus on ideas, to focus on the novelty of thought and idea, rather than trying to beat the world's largest, most industrial AI efforts at their own game. You know, that's just not going to be the way to move forward. But you know, the good news is we need more intelligence. We need more ideas. AI is not a solved problem. There are so many things that we could use help with, and there's so many opportunities for new ideas to change the way that we do our work. So, you know, the way that we deal with this question inside of the Nemotron effort is that we have scaling ladders. So there's a lot of different ideas, a lot of different ways of thinking about how to build technology for AI. And if there's some idea that has promise, like there's some interesting experimental results, there's an interesting theoretical justification for why that might be interesting, then we scale it up to the next level. We have a series of levels that get progressively more expensive and get also combined with other ideas. One of the challenges of this kind of research is that no idea is actually orthogonal. So in academia, we're taught how to do ablation studies to isolate the contribution of a particular idea. But when you're doing large-scale industrial AI, it's not about any one particular idea. It's about the composition of thousands of ideas to create the strongest possible AI that we know how to build. So those are kind of at odds with each other, right? Academia should really focus on individual ideas and showing the theoretical basis and showing some preliminary results that this is promising way to solve a problem. And then, you know, I would say work with industrial labs to get those ideas adopted. So that's how we do it inside Nemotron, and that's how I think the best AI research is successful today.
여기 있는 학생. 네.
Hi, I'm a undergraduate student in electrical and computer engineering. Thank you for your wonderful lecture. My question is about your research experience, especially about scaling laws. So you've mentioned that scaling laws were one of your main discovery at your time in Baidu. So my question is, as of now, scaling law seems like kind of obvious because it's like a bigger brain, bigger intelligence problem. But my question is, was that idea very obvious at your time? So like if you had a very clear vision about it, or rather it was just a vague hypothesis?
So first of all, I should say I am not the father of scaling laws. There are a lot of other people that really contributed to the creation of scaling laws in the way that they have really impacted AI. And you know, from a high level, it is kind of obvious. It does seem obvious, right? That like more compute, bigger data sets, better model, right? How hard could that be? On the other hand, there has been consistent doubt about that hypothesis in AI since time immemorial. You know, when I published my first paper at ICML in 2008, which was about training support vector machines on the GPU, people at the conference asked me why I was there. They said, why do you think it's important to train bigger models on bigger data sets? And back then in ICML in 2008, if you go back and read the conference proceedings, the vast majority of the papers were about fancy statistical methods, new ways of thinking about modeling, right? It wasn't about let's just apply more data and more compute. It was really about let's try to model things in a more sophisticated way. So there's always been this tension in the field of AI, like which one do we need, more brute force or more sophisticated math. And I think the scaling laws were an attempt to quantify how much we could get out of more compute and more data. Now, I've always believed, I started my career, just with this fervent belief that more compute, more data, bigger models was going to yield better results. Back when Jay and I met, I still believed that, and I wish that I had pushed that into a more formal statement, the way that the scaling laws folks did, because the power of the scaling laws is not in the high level understanding that more is bigger is better. That's not the power. The power of it is quantifying that in a way that allowed people to plan and then construct compute that was much bigger than they could have without that plan. Now, if you think about what it takes to build the world's most enormous data centers, we are entering an era where it takes gigawatts of power to run a data center. Do you know how much power a gigawatt is? Like, the largest nuclear reactor in the United States is about 4 gigawatts. We're going to have data centers that consume the same amount of power as an entire city. Do you know how much money it takes to do that? Do you know how much time it takes to do that? Do you know how much conviction it takes to build something that large? Without the scaling laws, it would be very hard to justify the investment that has been required for the development of modern AI. And so the insight really wasn't that bigger is better. The insight was, if I codify that and make it a very clear statement of how bigger is better, I can plan for the future and I can build something amazing. That was the thing that was so transformative about scaling laws.
Okay, maybe the student who wearing glasses. Like,
Hello, thank you for the wonderful lecture. I'm Jungwon Park. I'm a PhD student in artificial intelligence, and I would like to ask, what are the what are the challenges and difficulties that even the hybrid SSM and multi-token prediction that you proposed with the with Nvidia's model, all the even those models are currently difficult to solve, and what can be the potential solutions that can be taken to overcome those kind of challenges?
Yes, thank you. With the hybrid SSM models, we still do have a quadratic algorithm, right? So that's the thing, if you remember from your undergrad algorithms class, if you have a quadratic algorithm, it's still quadratic. Even if the scaling factor is very small on the quadratic part, it's still quadratic, right? So that is a challenge with the hybrid SSM architecture, as it is still a quadratic algorithm. And for very large sequence lengths, that can be very expensive. The second challenge has to do with state management. During inference, we have the KV cache and the SSM state that's associated with each query. It's very easy to run out of memory. And so more advanced quantization methods for that, and also partitioning methods, the way that we partition and map the computation of inference of a large language model onto a data center, I think is still rather an unsolved problem. Another challenge that we always face is the trade-off between single user throughput, which is often called latency, which I find very confusing, but let's say single user throughput and many user throughput. Now, for a single user, if you are, let's say, writing code and you're using a coding assistant, it feels amazing to have the results to your query come in at like 10,000 tokens per second, feels amazing. It makes you feel like you can do anything. You have so much force, so much power that you can direct. And if it messes up, no big deal. You throw out the part that messes up, ask it to fix it. It's very fast. You can iterate really quickly. Now, of course, the cost of doing that is much higher. There is always a trade-off that if we want to maximize the overall throughput of the machine, if we want to minimize the cost for every token that is produced for serving many, many users in the cloud, then we're going to actually slow down the response for a single user. And so trying to find a system that's good in both those things that compete against each other is still a challenge. The last challenge that I want to mention has to do with agentic systems. So the sequence length distribution for agentic systems is really different than the sequence length distribution that we've assumed for reasoning tasks in the past. In the past, we've thought about, okay, imagine that my AI model, its job is to take all of my emails, let's staple together all of my emails. This is my packet of context that I give the AI. And then I ask it a question, it's able to see everything I know, it's able to refer to all that. And then, it's going to reason and it's going to produce a result. But the way that agentic systems work is much less predictable. An agent, it's trying a bunch of things. So it's basically like, okay, try this, then execute it, which is outside the language model. It's calling something like a compiler or something, to run a program. And then it returns a result, you stick that into the language model, and then it has another thing to do, right? So the input and output sequence length distributions for agentic tasks, for agentic systems are quite different. And computationally, it's less regular, less uniform, less predictable, which then I think causes systems challenges for deploying agentic systems. So those are the top challenges that I see right now that we need to innovate on with the neural net architecture.
So we'll take just one more question before we actually do the lucky draw. So let's just one more. I see some locality here. I mean, since a lot of people, it's concentrated on this part. I think that the one white shirt, so he raised his hand multiple times. So I want to question from the last one.
Thank Bryan for the nice talk. I am Jaewon Jung, PhD student of electrical and computer engineering. My first question is about native multi-token prediction. As I know, in the past, Baidu developed Ernie model, the foundation model, and it already used multi-token prediction. So I'm curious because does the Ernie model inspire you? Or
Yeah, absolutely. Yeah.
I see. And thank you. And my second question is about fourth dimension of scaling law, because you mentioned about harness, agent harness, and I am curious. Do you have a plan to develop an open source platform for harness engineering?
That's such an interesting question. We do have a project called Nemotron, which is really about kind of an Nvidia opinionated way of setting up OpenClaw for agents. This question about harness engineering is something that we've tried to stay away from. What we want is for Nemotron models to be good in all harnesses. However, that may be somewhat impossible. It may be always the case that some harnesses work better than others, and it may also be the case that we want to provide custom harnesses for Nemotron to make it better at agents. I would say that's future work. At the moment, we're mostly just trying to make Nemotron as good as possible in all of the most important harnesses.
Thank you. So before we actually wrap up, we want to have the time. We want to have time for lucky draw, and then thanks to the generosity of Nvidia Korea, like some goodies, and then one more GPU to give up to students. So I think it'd be wonderful to to have this gifts awarded. So let's say let's start from the third. With the 5 goodies, like NVIDIA gift packages, 5 pieces of gift package. So can you please help us with the award, this goodies, and then let's see the result for the third prize of the NVIDIA gift package. If you see your name, can you please come front? If you see your name, please come. together four to be Okay, so there's one more winner. Okay, please. We actually have two winners, so we're gonna draw like three more people. 네. 혹시 이름이 어떻게 되시죠? 박지훈. 오케이, 박지훈 이상 두 학생 말고 저 세 학생은 다시 뽑겠습니다. So there are few people who are not here, so I think Okay, so can you do again? Yeah, so we're gonna have three more. Second round. In the first floor, please come. Oh, yes, I see. Two students are coming out. 정서윤, 위성현, 윤준헌, 최우혁, 신창민. I think we have like 5 people by now. So, anyone from the? No? Okay, I think we already have 5. Yeah, so please, you just get the. All right, so we actually have 5 people, 5 lucky people. Yeah, for time. Right? Thank you. We'll actually give it. Please take. Yeah, you can actually pick up your present from our staff. Thank you. All right. The next one is like a RTX GPU. RTX 5070, or that's what I remember. Yeah, so I think it's time for. Yeah, time for draw. So please. Next winner. Okay, these are like 20 candidates. 최화윤 학생, 최화윤. 혹시 최화윤 학생? 안타깝게도 최화윤 학생 자리 없는 것 같습니다. Okay, maybe we wait for like 10 more seconds. If she is not around, then maybe we just draw it again. Okay, congratulations for your getting like RTX 5070 Founders Edition GPU. And today's grand prize is the DGX Spark. So you can actually train your own model and you run your own model locally. So that'd be ideal machine. So today's a grand prize. So let's do the last lucky draw. (20명) 먼저 1라운드에서 박정영 혹시 1층에도 없어요? 네, 1층에도 없다고 합니다. 응용생물화학 학생이 없는데요. 오케이, 박정영 학생 없으시면 네, 그럼 다시 보겠습니다. 네, 다시 스피닝. Sorry, unfortunately, only those who are present here are eligible for receiving this prize. So I think, let's try again. 권호성. 저기 있습니다. 권호성. Let me just hear from him. 이걸로 what are you gonna do with it?
This is my 4th month since I started researching, but I don't have a desktop lab computer yet, so I'm gonna do research with this desktop computer. Thanks for this, your presence.
All right, thank you everyone for coming. This concludes today's talk. Thank you. Sorry. 잠깐만 저희 사진 촬영 한 번만 한다고 그러니까 죄송하지만 잠깐만 시간 되시는 분은 잠깐 앉으세요. Please sit down. Let's take take photo before your turn.
You say my name like it belongs. A quiet truth inside your song. No need for spark, no grand parade, just peace in what we've softly made. The world still spins, but I don't care. Your voice is home, it keeps me there through every noise, through every flame. You hold my heart when you hold my name. No more chasing what's already mine. I find my calm in your design.
A pair of jeans, a shirt or two. We didn't pack as if we weren't going back. It doesn't matter if it's true. I've got a feeling love will give us what we lack. The world is waiting up. The world is waiting half a step beyond our door. Yeah. And if it's not enough, I wanna see the stuff the world has got in store. I wanna take it all in, I'm falling. The cityscape by night, wanna catch in my photos. Where you go, every corner twice as bright. They'll be my treasures forever. When I can't hold you tight, I'll see the Stockholm lights. The Stockholm lights, the Stockholm lights. Tomorrow feels a year away, like the seconds, the beginning and the end. But if in time it's yesterday, your picture's gonna bring it home to me again.